If we can think of these various orbits in terms of relative energy, we can then come up with an energy diagram. In this particular case, the energy associated with the n equals infinity state is the zero value, which is the dashed line. The on the left here underneath the diagram for the atom is the equation for the various energies, and so it turns out that Bohr assigned the energy of the n equals infinity state as zero, and then we had increasingly negative values as you go down. So for the n equals 1 level, this is a situation which was the lowest energy situation, sometimes referred to as the ground state for hydrogen. And all of the other higher energy situations, n equals 2, 3, 4, all the way up to infinity, are referred to as excited states. The constant in this equation in your book is given in terms of joules rather than reciprocal meters, as we showed in the previous slide. So these are energy situations. Turns out then that if we were to add energy to the electron in the n equals 1 state, we can actually promote the electron into higher energy states. This has to be a quantized amount of energy. So if you don't put enough energy in to get it to at least the n equals 2 state, then the electron would remain in the n equals 1 state. And so that is a good example of the quantized nature of light and the electron. In this slide, we show the hydrogen atom and the various orbits, along with the energy diagram for any kind of electronic transitions that are involved, where the electron can jump from one orbit to another. In this particular case, we can cause a promotion of the electron from the n equals 1 level to the n equals 3 level by adding a photon of energy. It has to be a quantized amount of energy, so hence we think of this as being a photon, which is the particle nature of the electromagnetic radiation. But of course, the wave description says that we have both an electric and a magnetic component that is going to interact with the electron to impart this energy. So the photon strikes the electron, promoting it to the higher orbit. And of course, this can be demonstrated also in the energy diagram. So promoting electron from the so-called ground state to the excited state. Once the electron is in the excited state, it stays there for some period of time, but since this is not an energetically favorable situation, the electron will fall back down to some lower energy situation. It could fall back to the ground state, but in this case it has also the possibility that it will fall to the n equals 2 level. This results in the giving off of some of its energy in the form of photons or light, and if the light is of an appropriate wavelength, that situation for the transition from n equals 3 to n equals 2 happens to be the red color that we observe in the hydrogen emission spectrum for the Balmer series. It turns out that the energy of the emitted photon is therefore the energy difference between the two energy levels involved in the transition, and so in this particular case then it will be position where the final situation is n equals 2 and the initial situation is n equals 3. At this point, I would like to remind you about the relationship between wavelength, frequency, and energy for the electromagnetic spectrum. Turns out that as you decrease the wavelength, the frequency increases, so these two properties are inversely related to one another. In addition to decreasing the wavelength, you also increase the energy of the photons that are associated with short wavelengths. So it turns out that as you go from red to yellow to green to blue and violet, you have an increasing amount of energy associated with each of the photons in the line spectrum for hydrogen. And of course, this has to do with the gap in energy for the various energy states.